Okay, welcome to the second episode of guide sheet number 4. In this case, number 3 here, we're going to break down a vector into two perpendicular components along the x and y axis. So in each case, the vectors are not along x or y, and we'd like them to be, because then we can add all, if we're adding them, we can add all the y's together, and we can add all the x's together, and we can figure out a final result. So one of the things we have to be able to do is break a vector down into two components, and we want those components to be perpendicular or at right angles. Now I would refer you to the formula sheet. Under vectors, we have c, or the hypotenuse. We have an angle here, theta. We have this side, which is A, and then that's the adjacent side or touching side to the angle, and then B, or the opposite side. It's on the other side of the triangle. Pythagorean theorem would say that a squared plus b squared equals c squared. We've used that already. And then SOHCAHTOA would say that the sine of the angle theta is equal to the opposite side, the ratio of the opposite side over the hypotenuse. And the cosine of theta is equal to the adjacent sine over the hypotenuse, and the tangent of theta is equal to the opposite over the adjacent. So whenever you're working through these, if you need a place to refer to, go back and take a look at that sheet. The information's there. Okay, so I've got 12 meters. It's a distance, and I'm going to, displacement really, it's a vector, and I'm going to break it down into two components. The components I'm going to break it down into are going to be along the x and then the y axis. So vertical and horizontal. Now, to get this red side here, this is the angle, so this would be theta. This side from cosine is equal to the adjacent divided by the hypotenuse. If I want to solve that for the adjacent side, this side, which I would call displacement in x, is equal to the cosine of theta times the hypotenuse. So the distance in the displacement in x is the cosine of 30 degrees times 12 meters. Again, if you're working with a TI-83 or any of those graphing calculators, I would make sure you're in degree mode when you're working with these, because everything we're doing is in degrees. And then I'm going to multiply cosine of 30 times 12, and round it off no more than 3. I should probably round off to 2, but we'll go with 10.4 meters. Then for the blue side here, that's the opposite side of the triangle. So would tell us that the sine of the theta is equal to the opposite side divided by the hypotenuse. So if I solve that one for the opposite side, I'm going to get to dy is equal to the sine of theta times the hypotenuse. And again, you can see both of those relationships on the formula sheet. Okay. So in this case, it's going to be the sine of 30 degrees, which is 1/2, times 12 meters, gives us 6 meters. Okay, now you can always check yourself. You take 6 squared plus 10.4 squared, take the square root of that, you should be back to 12. So we've broken it into two components. In the next one, we'd also want to do the same thing. We'd want a vertical component. Now this time the vertical component is going to be going downward. You might think of that as negative depending on your coordinate system. And then the x component is going to the right. Now this is a nice angle in that it's 45 degrees. The cosine of 45 is 0.707, and the sine of 45 degrees is also 0.707. They're the same. So the two legs here, the red and the blue, will be the same length. To determine the amount, this case, this is touching, so I'm going to use the cosine of 45 degrees times 14 meters. So cosine of 45 times 14 gives us 9.899. That's going to be 9.9. And I don't have to recalculate because the angle's 45. This side here, the dy, is also going to be 9.9 meters. Now it is down. If I go to add that to something else, I'll have to keep in mind that that's pointing at 270 degrees. And they might actually end up subtracting. We might add a positive to a negative. In this last one here, it's the x direction that is actually negative, or to the left, and the y direction is also to the left, so we're down and to the left. Now, what angle do I use? I've got the angle reported from counterclockwise notation, 240 degrees. So when I'm using SOHCAHTOA, I want an inside or interior angle to my triangle. So I really want this angle here. Now, straight down is 270. So 270 minus 240 would make that angle 30 degrees. So sometime what you have to do is determine the angle that you really need by looking at the situation. So don't just think you're going to use the angle that's reported. You want to use an interior angle to the triangle. Okay, this is the touching side, so I'm going to want to use cosine of 30 degrees times 12. We've actually done that one already. That's 10.4. And then the red one down here, the horizontal axis, we're going to use sine of 30 times 12. That's going to be 6. Notice this time we're looking in the x direction, but we're using sine. This time we're working in the y direction, but we're using cosine. So it's not that you always use cosine in the x and you always use sine in the y. You have to determine which is the adjacent side and which is the opposite side. So you really kind of need to draw a picture each time, make sure you're got everything oriented right, and then use one of your angles to figure it out. Okay, and this time we're going to add these three vectors together like we showed in the first episode. But to get that resultant, which would be from where we started to where we finished, and these are the two resultants and what they're going to look like. We're going to break this one vector down into its two components. So I'm going to figure out how much of this vector goes to the right and how much of this vector goes up. And that'll allow us to add this together. Now this is 30 degrees at 12 meters. We've already done this up above. I'd refer you back to this section right here. dx is going to be 10.4 and dy is going to be 6. So this is 6 meters, and this one down here is 10.4 meters. Now, once I've broken this vector down into two perpendicular components, I am going to get rid of it. Okay, you don't use both the vector itself and the two components. You use either the components or the vector itself. Once you've made your breakdown, once you've gotten that one vector into two components, you're not going to use that vector anymore. So mark it out, make it clear to yourself it's no longer part of the program. Okay, so now what I actually have here is, if I redraw the perpendicular components, I have a 5 meter long component, I have a 10.4 meter long component, and I have a 4 meter long component. The only vertical that I have is 6 meters. So my resultant, which this time I'll put in black just to differentiate the color, is going to be made up of, this is 5, this is 10.4, and this is 4. They're all in meters. So that's 14.4, 19.4 meters. This one is 6 meters. So this is going to be the square root of 19.4 squared plus 6 squared. That is a right triangle, so a squared plus b squared will be equal to c squared. Or c will be equal to the square root of a squared plus b squared. So 19.4 x squared plus 6x squared. Take the square root of the answer, and we get 20.3. And that's in meters. And we'd also want to figure out this angle. I like to again use inverse tangent of theta. Again, what I'm doing is asking the calculator to tell me what angle goes with this ratio, the opposite over the adjacent. So it's going to be the inverse tangent of 6 divided by 19.4. And we're looking at about 17 degrees. So the final answer for our result is 20.3 meters at 17 degrees. For this next one, same thing. Here's our 14 of 45. Now again, we did that one up above. So if we go back to there, we got 9.9 and 9.9. So that breaks down into a vector of 9.9 this way and a vector of 9.9 this way. Now again, I'm not going to use this vector anymore. I'm replacing it with the two vectors to make it up. This is the resultant that I'm going to end up with. But I'm going to redraw everything so it's ordered, and I can create just a simple right triangle. This time I have 9, and I have again, that one's worth 9.9. So I have a 9 and a 9.9. They both go to the right. And then I have an up 5 and a down 9.5. Now, 9.5 minus 5, 9.9 minus 5 is going to be 4.9. So then I'm going to have a vertical downward because most of the vector is downward, the majority of it. And that's going to be 4.9. So I've got a 4.9 meters here, and I've got this is 9 and this is 9.9. So this was 9.9 meters. This was 9.9 meters. And the resultant vector then is the vector from where I started to where I finished. And again, I don't want to figure out the value of the resultant, so it would be the square root of 4.9 squared, and then 9 plus 9.9 is 18.9 squared. 4.9 x squared plus 18.9 x squared. We're looking at 19.5. That's in meters. And then theta is going to be the inverse tangent of 4.9. That's the opposite side, divided by 18.9. Meters cancel out. Second function, inverse tangent of 4.9 divided by 18.9. And we're looking at about 14.5 degrees. Now again, for counterclockwise notation, I should subtract that from 360, and report it as 19.5 meters at 346 degrees, running off to 1 degree, and that's the final resultant displacement. Okay, so that's how you would add and work together with components and breaking down into a component. You didn't have to draw anything to scale. Everything was figured out mathematically. And that's the end of guide sheet number 4.